This video is to introduce our work gradient-based algorithms for machine teaching. This work is done collaborated with Kabir and supervised by Nuno. This year, many large-scale datasets were proposed almost on a vision task. People have found that training on a large dataset can always bring about performance improvements. Many breakthrough methods proposed also are thanks to large available datasets. This dataset usually contains every object, action, or things, and can be scalably annotated on crowdsourcing platforms such as Untitled. This is, however, usually not true for fine-grained expert domain. While data collection can still be easy, but annotation is hard because it requires specialized and domain-specific knowledge. This makes it hard to collect a large dataset and is hampering the development and application of computer vision in this domain. For example, even the new largest biological dataset on naturalist only contains fewer instances than ImageNet proposed about 10 years ago. This has motivated extensive research in alternative and less label-intensive forms of learning, such as fusion learning, transfer learning, semi-supervised learning, and self-supervised learning. However, these approaches usually underperform supervised learning, especially on fine-grained domain. In this paper, we adopt another solution by machine teaching. That is to automatically design courses to teach real humans to learn some knowledge and concepts. The basic idea is when we collect a large number of raw data, we ask the domain expert to label a small number of data. Then we train a classifier on it. We use a machine teaching algorithm to generate a course and teach human learner where they can be online annotators. Then if this annotator learns the concept, they can label more data. In this case, we can obtain a large number of annotated data and train a supervised model. The formulation of machine teaching can be summarized like this. It's assumed that the teacher can access a larger dataset D, here dataset that the domain expert labeled. From this dataset, the teacher ensembles a small ordered subset L, usually called teaching set, where student learns and trying to achieve the best trade-off between learning the optimal predictor on D and spending the least amount of effort. The widely adopted strategy is using a network to mimic human behavior, and then the samples are selected according to this simulated human. In this process, we need to think about how to model humans, different from existing work that is based on suboptimal student assumption that humans have limited capacity. We argue that the algorithm should be designed from optimal student assumption on crowdsourcing scenarios from three considerations. First, because the course for annotator should not be difficult, otherwise the worker would reject to do it. This enforces us to have to simplify the course and makes the teaching sets small. If the size of the dataset is small, we think humans should handle it perfectly. Second, optimality always holds machine learning students. We think it's sensible for human students who usually do not underperform machine learning students on few-shot learning scenario in practice. Third, works are free-wheeling participants and rated by their task performance, so they will try their best to complete the task. In this work, we adopt the iterative learning manner. At each iteration, the teachers select new example from a large dataset to complement the small teaching set usually by students to learn a task. Examples are selected by comparison the current student model to the optimal model for the larger dataset. The optimal student uses the teaching set to update his or her model and feedback its prediction to the teacher. So the core is how to select the new example. In this paper, we argue that the optimal example should be the one that can maximize the gradient if the student network trade on it and consequently speed the learning process. So we name it MaxGrad. Look at this picture for the main idea. Because the teacher can access the large dataset D, so it knows the gradient, but students can only learn on the selected small teaching set. So we augment the teaching set with a new example that makes the gradient as close as possible with the gradient of the teacher if students trade on the augmented teaching set. The derivative can be found in the paper and supplementary materials. We evaluate our method on two benchmarks. We first evaluate on simulated students where the networks are used as students. After teaching the students with 20 images, our max grade can reach higher testing accuracy, for example, about 65% on butterflies. When students is real humans, we also got better performance and know that 80% on butterfly, higher than 65 on simulated students. This also comes from optimal student assumption. Codes are available online. Thank you.